and also from Cornell University. And today his the title of his talk is Quantum Algorithm for the Ground State Energetics of Strongly Correlated Molecules. Professor Maitra, the windows is yours, please.
Thank you. Thank you, Dr. Nitik Mukherjee. And I thank the organizers. Let me before that share my screen. Just 1 second. Yeah, you can all see it. Can you see my screen?
Yes.
Okay. And is it? Can you see the full screen mode?
No, it's not in full screen mode.
It's not in full screen mode yet. Okay. Yeah, can you see it in the full screen mode now?
Yes.
Okay, right. Okay. So let me thank the organizers for inviting me to present in this summer school on quantum information and quantum technology. So I will be talking about a bit more technical than what the previous speaker Sangeeta has already talked about. And I will be talking about basically a few algorithms that we use or part of which we develop also for the ground and excited. I'm not going into the excited state energetics today of some molecular systems. And being a chemist, we specifically are interested in atomic and molecular system, particularly the many-body electronic structure of atoms and molecules. And there are certain class of molecules or certain regions in a molecular potential energy surface. For example, the bond dissociation limit, or some say strongly interacting systems where actually the system poses severe challenge for any conventional electronic structure theory. So these are the class of strongly correlated molecules. That means it's a very strongly interacting set of electrons are there. And this is what happens, for example, in the place of bond dissociation, say diradicals and all this kind of stuff. So I will be talking about a couple of quantum algorithms. By quantum algorithms, I mean, of course, they are all quantum mechanical theories, but which are implemented in a quantum computer or a quantum simulator. And this is a fairly new field. So many of these works are at its infancy, and I will be talking about some of these latest developments from our group. So before that, now that Sangeeta has more or less spoken about what is a qubit and what are the quantum gates, this makes my presentation much simpler. So as you have all seen that the quantum computers are those which operate based on the laws of quantum mechanics, and they offer great promise in handling certain problems which are intractable in doing any classical computer. So the basic unit of a quantum computer is called the qubits, which is taken as the basic unit of quantum information. And what is a qubit that Sangeeta has already talked about? That's basically a superposition of bits. That means you have an on state and an off state. For example, a switch, you have an on state and an off state. The qubits are any linear combination of any normalized linear combination of this on state and off state. So if I have a state 0 and if I have a state 1, you can make any arbitrary linear combination, and that is to be represented as one qubit. For example, I can talk about any two-level system that can be represented as a qubit. For example, the occupancy in a spin orbital, which can be either 1 or 0. It can be the polarization states of photons, or many different two-level systems. And then in a quantum computer, what happens that these qubits are connected through certain operations, certain gates, like a classical circuit, which are called the quantum gates. So what is a quantum gate? A quantum gate is a unitary operation. And due to the unitarity, by construction, they are reversible. I have just given one particular example, and they have all their particular functional forms. And I believe that you all know what is a unitary operation. The question that we ask now is that, can we simulate molecular energetics on a computer, on a quantum computer, through these two building blocks, that qubits and the quantum gates? So first the algorithm that I will be talking about is called the full configuration interaction algorithm. What is that? It's a quantum mechanical algorithm, but implementation of this algorithm in a classical computer, that is exponentially costly. For example, if you have n number of electrons in a system, and if you have a k number of spin orbitals, each spin orbital can have a occupancy 1, then n number of electrons in the system can be spanned in k number of spin orbitals, assuming of course k must be greater than n. You can span this in kcn ways. All right. So there is a large number of, and as you grow the number of k, this scaling goes drastically very high. So this is beyond a very small size chemical systems, atomic or molecular size, for example, say 4, 5, 6, or at max 8 or 9 electrons. You cannot really do an exact quantum mechanical calculation in this classical algorithm, which is called the full configuration interaction. All right, because of the exponential large scale. But the algorithm that I am going to talk about today is called the quantum phase estimation algorithm, which is you can take as a counterpart of the full configuration interaction algorithm. And I will be talking about some of its pros and cons and how to overcome these cons when I will be talking about the quantum phase estimation algorithm. The advantage of using this quantum phase estimation algorithm over the classical algorithm is that it has a polynomial scaling. That means it scales polynomially with respect to the system size k, which is not the case for any classical algorithm. What is that? So the aim of this entire exercise, the quantum phase estimation algorithm, first I will be going about the known algorithms, and then I will be going into the unknown domain. It is basically to estimate the energy spectrum of one at a time of a given physical Hamiltonian. That means I have a many-body Hamiltonian, I have the kinetic energy term, I have the electron-nuclear attraction, and I have the electron-electron repulsion terms. And due to this electron-electron repulsion terms, the exact eigenfunction of this one is you cannot really do an eigenvalue equation without any sort of approximation. So given the fact that I have a very good approximate wave function, which is the eigenfunction of this physical Hamiltonian, how to extract the corresponding energy? So this phase estimation algorithm, what it does is that it extracts the energy in terms of its phase. How is it done? So suppose I have a unitary operator, it comes directly from your time-dependent Schrodinger equation. This is an unitary operator, it's minus IHT. And if you evolve this operator in time, and when it reaches the stationary state, you get the corresponding energy E of the system, such that the energy E is the eigenenergy of this physical Hamiltonian that we are talking about. And since this is a periodic function, I can write down this energy in terms of my phase, assuming t equals to 1. How do I extract the phase? This phase is basically extracted in terms of a certain number of binary digits. So this, you see that this phi1, phi2 up to phi m. So I have n number of binary digits, 0 or 1, and you can construct any irrational number with these different combinations of this binary digit. So I have a string of length m of binary numbers 0 and 1, and the number n, that how long the string is, that is dictated that how much precision that I am going to I'm going to extract for this energy. So my precision of determining energy is pre-decided. Okay, so the algorithm that I'm going to talk about is called the iterative phase estimation algorithm, where the number of iterations that dictates how long this string is going to be. So if I have an m iteration and I'm going to iteratively sort of construct this string of binary digits, I'm getting a phase of m precision in binary digit. Now, this is done in a quantum computer using an unitary operator U, and this uses two particular registers in a quantum computer. One is called an ancillary register. I will show a circuit in a moment. And the other is called a wave function register, where you are dumping your wave function in terms of its occupancy. So for example, you have a certain orbitals occupied, and suppose you name your orbitals from 1 to k, and you know what is the occupancy 1 0 0 0 1 0 whatever be the occupancy. And then comes the quantum circuit, how to extract this one. It's going to be a bit technical for the next 3-4 slides, but you will enjoy it. So this is typically a quantum circuit that we talk about for the phase estimation algorithm. This is the wave function register. Sorry, this is the wave function register where I store my wave function, and this register corresponds that number of qubits. What is the total number of the spin orbitals in my system? And I have one single ancilla qubit where I will measure the phase. So what we do, we apply some basis changing operation. This is called a Hadamard gate. We apply this basis changing operation on the qubit, and write, if we measure it at this stage, what we get is a linear superposition state of 0 and 1. Then what we do, that depending on this wave function, the qubit it acts on, it gives a unitary, it gives a controlled rotation, which is an unitary operation. It gives a controlled rotation, and the controlled rotation does something which is known as the phase impact, which I have shown elaborately in these two circuits. So what it does, see that this stage, if we do a measurement, it has 0 and 1. So if this is 0, this remains unchanged. That's the controlled operation. If this is 1, the phase here is kicked back onto this register, on the ancilla register, and the phase is something this. So I get again a linear superposition of these two qubits 0 and 1 with a given phase factor that has been kicked back onto the ancilla qubit. Now I transform it back to the basis that I started my computation with, which is called the computation basis. And if you do a little bit of algebra, what happens that if you do the measurement at this stage, that's what I have done here, you get a linear superposition state here where the probability of getting this phase 1 is the square of this quantity, and the probability of getting the phase 0 is the square of this quantity. And depending on which qubit I measure at this position, I can extract the phase from here. So that's the basic structure of a quantum phase estimation algorithm. I will now show very briefly that how to use this one in a quantum computer to extract the molecular energetics. I can start with an arbitrary reference function. I call it the arbitrary reference function. And since my Hilbert space consists of n electron is complete, I can write any arbitrary function as a linear combination of the eigenfunctions of the corresponding Hamiltonian. So this psi1, psi0, psi0, these are the eigenfunctions of your Hamiltonian, where psi0 gives you the ground state, psi1 gives you the excited state, psi2 gives you the second excited state, so on and so forth. And suppose I have just this three-dimensional system. I have these three sets of states, which are the eigenfunctions of my Hamiltonian, and I would like to extract the eigenphase of the corresponding ground state to a given degree of precision. This, how much degree of precision I want to extract, that is pre-decided, and that is decided by the number of iterations I will do. So suppose I'm just taking a very toy example just to make you understand all this machinery. It's a very toy example, it's not the exact thing. Suppose the ground state phase is something like this. Say, see, I have written it down in terms of zeros and one. This is the binary bits, precise up to 3 digits. I have the first excited state bits 0, 1, 1. Second excited state bits are 1, 0, 0. The measured bits are 1, 0, 0. And what we do, I first measure the least significant bit, that is phi naught. Then I measure the second least significant bit phi 1, and then so on and so forth. Then I finally measure the most significant bit phi 2. So I measure it from this direction to this direction. So I am doing a 3-level system. So that means I have ground state and 2 excited states. I'm measuring it up to 3 significant digits. Fine. Now, how do I do that? Suppose I have this linear combination and this is the phase bits that I am going to extract. What happens once I do the measurement of this first least significant bit, that is phi naught? What happens is that this phi naught may appear, these bits may appear in alpha naught and alpha 1. So I have ruled out the possibility that I cannot reach the second excited state, which is psi 2. So basically, I narrow down my search probability from these 3 states to 2 states. I measure the second least significant bit. What is the probability of second least significant bit? You can get either 0 or you can get a 1. And suppose I measure it to be 0. Then I am ruling out the probability of reaching psi 1. And finally, the third bit, once I measure, that becomes deterministically 0, and I get the exact bit for psi naught, which is my ground state of the system. So basically, starting from the least significant bit, I can construct the algorithm in such a way I can rule out the possibilities of reaching out different excited states. And finally, I land up to the state that I desire for. This is the typical algorithm for what is called the phase estimation algorithm, iterative phase estimation algorithm. But this comes with a price. The price is that the probability of success of this algorithm, that you can reach the desired eigenstate, that is dictated. If you see this little bit of algebra here, the probability of extracting the bit corresponding to the ground state, it is given by the coefficient of the ground state, this squared of this quantity. That is, this C naught is simply the reference function with an inner product with the target state that I am targeting to achieve, the phase of which I am targeting to achieve. All right. So you need to have a state that has a reference state that has sufficiently close, sufficiently high overlap with your target state, such that you can reach this desired eigenphase in an more or less very deterministic manner. It's all probabilistic, but in a more reliable manner, I would say. So the success probability is basically defined by the square of the overlap between the reference state and the target state. All right. Fine. So the algorithm depends on the closeness of the initial state to the target eigenstate. Of course, if I can reach the target eigenstate starting from any arbitrary reference state, the measured energy remains invariant. There is no change in the measured eigenphase. But whether you will reach that particular target state, that depends on the success probability. And here comes the problem. I can take with the simplest choice, which is called the Hartree-Fock state. What is a Hartree-Fock state? Suppose I'm taking a very toy example. I have 4 hydrogen atoms on a circle. And this is a very typical case of a molecular strong correlation, where you change this angle beta. And around beta equals to 90 degrees, around this region, there are 2 electronic states which become very close to each other, energetically very close to each other. And that makes your life very difficult because of the fact then you cannot start with any of these determinants to reliably reach the exact correlated eigenstate of the system. So what is the simplest choice that I can start with? The simplest choice is called the Hartree-Fock state. What is a Hartree-Fock state? You have an optimized state which takes care of your exchange correlation, where the lowest spin orbitals in a state, in an atom or in a molecule are occupied. And I mean, filling up in terms of the Aufbau principle, and then there are remaining unoccupied states. So the left ones are my up spin orbitals, the right ones are my down spin orbitals. So the up spin orbital and the down spin orbitals stemming out from the same spatial orbitals, they are shown to be degenerate. So this will be a typical occupancy. And this is the typical Hartree-Fock state. Now let me do a phase estimation that I have shown you through the circuit before. Let me do a phase estimation and try to reach the correlated ground state. What happens? suppose my exact energy, which I know, I chose a system in such a way for which I know the exact energy. This exact energy is somewhere here. All right. Don't go over to this. What are these shorts right now? That I will. Okay, I can just briefly introduce this one once. Just going back. So see that this measurement of these bits phi naught or phi 1 or phi 2, these are all probabilistic. So if you do a very few number of measurements, it's like tossing a slightly biased coin. Suppose you have a bias on head over tail, but if you just toss it once or twice, you can still get tail. But if you toss it some hundred thousands of times, you will get the head exponentially large number of times over tail because you have a bias on head. So if I have a bias over state 1 or state 0, if I do this measurement many times, then the unbiased state, the probability of reaching the unbiased state goes exponentially low. So that's a theory of the probability. This is called there is a famous limit in statement also in this. So what I do is that if I want to reach some states for the correlated ground state, which I'm expected to reach somewhere here. But if I do this measurement, since this is probabilistic, I repeated these things 40 times with different number of measurements of these phase bits. And each time this phase bit, I measured this phase bit 25 times, I measured this phase bit 50 times, and each thing is repeated, say 40 times in this box. So all these 40 repetitions in this box have been done with measurement of the phase bits 25 times. All the repetitions, 40 repetitions in this box are done with a measurement of the phase bits 100 times, so on and so forth. So you see that as I make the theory more and more reliable with large number of measurement of these phase bits, what I reach here is some sort of an excited state somewhere here. So I cannot start with an Hartree-Fock state because I cannot extract the energy of the ground state starting from the Hartree-Fock state because it takes me somewhere to the excited state because of the fact that this overlap problem. That this excited state is probably having a much larger overlap with the Hartree-Fock state. But I can tweak the algorithm. What algorithm I can do? I can generate an algorithm which is called a variational quantum algorithm, which is basically, you might have heard the term already, which is basically, I can prepare a state, a correlated state in such a way through a very shallow depth circuit such that I can prepare a state through a trial, through a sort of a semi-optimization of the energy. What is this variational algorithm? I will come later in the point in this talk. And then this state that is prepared through this variational energy minimization that is fed into the as an input state of this phase estimation algorithm. And then, sorry, this is somewhere here. So what I do here is that I construct a quantum circuit here. I optimize the circuit with respect to the different parameters. And I minimize this energy expectation value obtained from the Hamiltonian averaging. And then a semi-optimized state is then thrown into the input state of this IQPE algorithm. So this yellowish part is my IQPE algorithm that I talked about. And this is my variational quantum eigensolver that I am using to prepare my state. I input as an Hartree-Fock state. I evolve this state through some variational optimization. I do this optimization and throw in this optimized state into this IQPE algorithm, such that the input state at this stage will have a certain overlap with the exact eigenstate of the system that I'm going to measure. So again, I'm going over to the H4 on a circle model that I talked about. And what the variational algorithm ansatz that I took, I call this one, which is called the unitary coupled cluster ansatz. What is that? I'm not introducing it right now. It uses an unitary parametrization in terms of your excitation operators. The excitation operators are written in second quantized notation, where these thetas are basically my unknown parameters. And I have a string of creation and annihilation operators, which I map through some sort of a Jordan-Wigner mapping or a Bravik-Kitaev mapping or some other mapping into a string of qubit operators, mostly in terms of the Pauli's spin matrices. And then with this kind of an unitary operator that I have constructed through this Jordan-Wigner transformation, I construct this energy functional and variationally optimize this energy functional with respect to the parameters. This is the basic algorithm of the VQE. Now, what happens if I do this kind of an algorithm? Suppose I'm talking about a state where this beta is very close to 90 degrees. Say I'm talking about 89.8 degrees. See, this is when my number of VQE iterations is 0. This is my VQE iterations. When my number of VQE iterations is 0, that is basically my Hartree-Fock state. In this state, you see that these two plots, so basically this one, the upper one is the psi target and overlap with psi excited squared. And the lower one is psi, I'm sorry. The ground, this is ground. And the lower one is psi target overlap with psi excited squared. So what happens around this, you see that the Hartree-Fock state with 0 iteration, both the overlap with the ground state and the excited state, that is actually almost same. So the measurement every time probabilistically takes me, starting from a Hartree-Fock function, takes me to the excited determinant. But if I do this number of VQE iterations, so that means if I do this optimization, I don't need to reach this exact minima. I can do it some number of times. And if I do it just a few number of times, you see that the overlap with the target state, the ground state with the initial state, and the overlap with my initial state with the excited state, not that this should not be the target state, that's the initial state. This is also the initial state. The initial state that I'm preparing through VQE. So this probability is actually increasing nearly to 0.9 or 0.95. And this is probabilistically going down almost to 0. That means I have now prepared a state which has a much higher success probability to reach to my target ground state through the IQPE algorithm. So if I optimize this system, say at this state with say 4,000 iteration, it is not yet reached the exact energy minima. What I reach, I need a fairly well prepared state which has a very large overlap with the target ground state. And let me do the measurement now. So this was what I obtained from starting with the Hartree-Fock state. And this is what I am doing it with a certain number of states prepared with 200 variational eigensolver algorithm, 1000 and 3000. And every time you see that I reach a state with every 40 repetitions of my experiment, I reach a state which is exactly onto the full CI state. What is about the potential energy surface? The potential energy surface, as you can see, that this is my exact potential energy surface, which is basically my full CI. If I do this variational optimization till its convergence, if I do the variational optimization till its convergence, that means when this quantity, this thing is satisfied, but no IQPE involved, I reach a state which is having a fairly large cusp or kink around this region, but I can prepare this state in a much better manner through this VQE algorithm, throw it as an input state to IQPE, and you see that I reach a state which is exactly very, very close to the full CI state with very less non-parallelity error. What is the accuracy or what is the gap? That is determined by what is the length of this bit string that I have measured. That is determined by this M that I introduced much back. So every time, the point is that every time I reach my target eigenstate, which is the ground state of my physical Hamiltonian. Fine. But this, I cannot have a method which has the state preparation itself is costly or exponentially costly. I can start with a classically prepared state also, but you see that sometimes the classical prepared state, which is called a CI algorithm, it scales exponentially large. So I cannot afford to have a state preparation for my IQPE algorithm, which itself is exponentially large. So I want to further reduce this cost for the state preparation. And let me do it in a different way. So I can use my chemical intuition here. What are the two states that comes energetically close when I have beta equals to 90 degrees? When is beta equals to 90 degrees? I said that I have two states which are energetically very close. What are these two states? What are the configuration of these two states? These two states are, this is the Hartree-Fock state, you can see, and this is a state where two of these electrons have been excited from here to here and here to here. So I can think of this region as my Fermi, around the Fermi level, and this region as my chemically active region, which is basically spanned by HOMO and LUMO. You see, I have shaded this region, which are basically spanned by HOMO and LUMO orbitals. And I can actually construct these two degenerate determinants, or at least quasi-degenerate determinants, by exciting the electrons from the HOMO orbital, the highest occupied molecular orbitals, to the lowest unoccupied molecular orbitals. And I don't really need to have the excitations involving 3 or involving 0, because these are chemically inert orbitals, 3 or 0. So I can, in principle, restrict my ansatz or restrict these T operators in a much smaller space. And the smaller space is encompassed just in this shaded region, which I call as an active space. So I don't need to use this full algorithm here, full T operator here. I can use a very subset of these T operators, which I call the active T operators, active T2 operators, involving just these two sets of orbitals. And I can prepare the state such that the state is, and I am preparing the state through this variational quantum eigensolver, and the state is something, a linear combination of this Hartree-Fock determinant and this quasi-degenerate determinant. And I don't need to take care of any other excited roots which involve 3 or 0. Let me do what the measurement now does. I prepare this state, which is basically a linear combination of this plus this, and I throw in this superposition state into my iterative quantum phase estimation algorithm. And you see, again, every time I do this measurement, I repeat this experiment 40 times. All these 40 repetitions produce the result, which is exactly same as the full CI. So this is the summary of this result, that starting from any arbitrary state, say Hartree-Fock state, in a strongly correlated regime, it takes you probabilistically, it may take you probabilistically to an excited determinant. You cannot really determine a ground state energy in a guaranteed manner starting from an Hartree-Fock state. You will have to prepare the state in such a way that it takes care of at least a few of the relevant determinants, which are actually important in your ground state wave function. And that is what we did through this active space thing. And every time I do this repetition of this experiment, I measure the exact full CI energy precise up to the number of bits I wanted for. And this is already, we have circulated this one. This is available in this archive. You can have a look if you are interested. I'm just going to talk about very shortly about the resource requirement. And you see that the NO is the number of occupied orbitals, NV is the number of unoccupied orbitals. You can see that I had 4 occupied orbitals, 4 occupied spin orbitals, 4 unoccupied spin orbitals, and the full space ansatz required this number of parameters, of the order of this number of parameters. And you can see that active space is of course much smaller than the total number of orbitals. So restricting this thing to only the active space, the ansatz to only to the active space, I can cut down in the number of parameters and the number of quantum gates in my state preparation. But at the same time, you are guaranteed to reach, at least for the system we studied, you are guaranteed to reach the exact eigenstate of your physical Hamiltonian. All said and done, in the last, say, 15 minutes or so, I will go into more into this IQPE, into this VQE algorithm that I talked about. The problem of this phase estimation is that this is beyond the reach of any NISQ device. You must have heard the term that NISQ device. What is the NISQ? This is the noisy intermediate scale quantum device. This requires, as you have seen, that this requires some controlled operation, the controlled rotation, which kicks back the phase of your exact wave function onto your ancillary wave function. So this one actually results in very high gate depth of your IQP part of the algorithm. So the IQP algorithm is formally correct. It is exact in principle. The problem is this is probably beyond the reach of an NISQ device. But can we take, the question is, can we tailor our VQE answers in such a way? If I just go back a few slides, you see that at this stage of my algorithm, I can minimize the energy to get the converged values, but the algorithm is not, I mean at least the answers or the operators that I have taken, they are not so precise that I can reach this full scale energy with utmost precision. I have a substantial energy gap around this region, which is the strong correlation region. Can I tweak my, can I make my ansatz better such that within this variational quantum eigensolver framework, I can reach the exact energy? So in other words, you need to make variational quantum eigensolver, the ansatz to start with variational quantum eigensolver, more expressible. That means it should be able to span at least the entire part of your n electron Hilbert space. How do I make my ansatz? You remember that I have taken an exponential ansatz, exponential of these excitation operators. And this is not something called an expressible ansatz. This is not an expressible ansatz because it does not span the entire Hilbert space. To make it span the entire Hilbert space, I will have to redesign my VQE ansatz. And what is that? I will go to that one. So my target is now to bring in the expressibility in my quantum ansatz, which will be able to span the n electron Hilbert space. But at the same time, it should not be so expressible that I have a very, very large quantum circuit or very high quantum circuit. You cannot increase your circuit volume to a great extent to compromise, to accommodate the expressibility in your ansatz, because you see that more expressible an ansatz is, it becomes less trainable. That means if you try to span the entire n electron Hilbert space, your optimization probably takes exponentially large number of steps to come to an energetic minimum. So most expressible ansatz that comes with a huge circuit depth. So you need to strike a balance between the expressibility and the cost of the implementation. Fine. What do I do? Suppose this is the ansatz that we talk about. Suppose if you truncate these T operators to only T1 and T2, that means you have the one body excitations and the two body excitations. And if I do this and I construct this energy functional, and if I do this del E del theta going to 0, that will give me my converged parameters, and then I can construct the energy. But if you increase this T1, I mean this T operator to one body, two body, three body excitation, four rank excitation, you see that an n-tuple excitation has a very, very large computational scaling because the number of parameters gets very high, exponentially high, because it comes as a power of n. I want to restrict it. I want to go beyond two body operator. And here comes my many body picture and the quantum chemistry that I am going to introduce into quantum computing domain. I can bring in some other operators S, which I call as a scattering operator. And this scattering operator acts on an entangled state. So basically, I have this operator, exponential of T1 and T2, acts on the Hartree-Fock state, and I entangle the qubits. I have an excited determinant where the qubits are entangled. And then on this entangled qubits, I again act on a set of the cluster operators. What do they do? First, I suppose I have this kind of a scenario. The Hartree-Fock state, as I have said, it's the lowest, energetically lowest occupied states. I excite two electrons from here to here. So by the action of e to the power t minus t dagger, I get a doubly excited determinant. And then my scattering operator, what it does, it scatters either within, so this is my unoccupied space. Remember, this is my unoccupied space. this is my unoccupied space. The scattering operator is such that it scatters an electron within this space and scatters and excites an electron from this orbital, this occupied to unoccupied orbitals. So it has a structure like one excitation and one scattering, one excitation, one scattering, and this thing acts on a doubly excited determinant. Why? That needs a lot of algebra and a lot of, say, what is known as the Wick's theorem. You need to employ what is known as a variation of the Feynman diagrams and what is called the Goldstone diagrams and many, many diagrammatic techniques and algebra. I'm not going into the details of the structure of the S operators. But what we do here then is the fact that I unitarize these operators into S minus S dagger. Forget about what is SH and SP. That's not your business right now. I have these T operators written in the unitarized form: T minus T dagger, T1 minus T2 dagger, T1 minus T1 dagger, T2 minus T2 dagger, and I call them tau or sigma. And then what I do, I write them in terms of a coherent time evolution, which is called the Suzuki-Trotter decomposition. Which is called the Suzuki-Trotter decomposition. Remember, when I prepared the circuit for VQE using this minimally parametrized active space ansatz or the full ansatz, I had to do this Suzuki-Trotter decomposition. I had not shown there explicitly over there. So I do a Suzuki-Trotter decomposition and then one by one act all these operators on the Hartree-Fock state, all the T operators on the Hartree-Fock state, and then all the S operators on the entangled state. So the total quantum circuit now looks like this. I have a Hartree-Fock state prepared here. I have an excitation operator. So this is basically e to the power T minus T dagger operation in this green box. Then once this is prepared, this is an entangled state right here. This is an entangled state. Then I write e to the power S minus S dagger operation. And then I do a measurement right here. So this green part is my quantum subroutine. And then I do this optimization in a classical optimization or optimizer through any sort of energy minimizer. For example, you can take it Kobila, you can take it conjugate gradient or any sort of gradient or non-gradient based energy optimizer. And I construct this energy functional and I variationally optimize it with respect to both the parameters in T and the parameters in S. So I variationally optimize with respect to both the parameters in an coupled manner. The new parameters that I obtained from this optimization, then they are fed back into the quantum routine. And again, this circuit is repeated n number of times until I reach my energy minima or until this condition is strictly satisfied. All right, so this is my grand algorithm, and this is something that we are currently working on. And we have actually worked on many different approximate versions, how to approximate these different S operators or different T operators. We have worked on many approximate versions, and each approximation actually cuts down in the number of your, I mean, not this, the names are not really important. They really cut down in the number of parameters, and the reduction in the number of parameters automatically ensure that you have a reduction in the number of quantum gate or in the depth of your quantum circuit, in the volume of your quantum circuit. So I have a number of variants that I have constructed from this theory. And coming back to result, and I have taken a slightly larger system this time, but still I know my exact calculation. And this is a water molecule. So the system is like this. This is oxygen, hydrogen, hydrogen. And I symmetrically stretch this one symmetrically such that the symmetry is preserved. And I see that as I stretch this one, how the potential energy surface works. So this is my Hartree-Fock configuration, you know. And the system is characterized by this 5, 6, 6, 6, 12, and there is one frozen. So basically 14 spin orbitals. And each spin orbitals is mapped into 1 qubit. So each of these are basically 1 qubit. If I do the conventional UCCSD1 that I talked about in the very beginning in the state preparation, you see as I stretch the molecular geometry, it is catastrophic. If I stretch it, say, for example, twice, so this bond length is twice the equilibrium bond length, the difference with respect to, look at the y-axis, this is difference with respect to my exact calculation. And this is catastrophic. It goes down, it goes anywhere. It goes much beyond your chemical accuracy. The chemical accuracy is the shaded region till here. If I do all our ansatz without much really increase in your circuit depth, you see that all of them are within this at max, this maximum error limit, which is basically in the range of some tens of microhertz. This scale is in millihertz. That's in some, just a few fraction or say tens of microhertz at max. I will show the non-parallelity error, and the non-parallelity error is basically the difference between the highest error and the lowest error in this entire potential energy surface. And you see that this non-parallelity error, the red dots in millihertz for the UCCD ansatz, it's somewhere here. It's much higher. It's about 5 millihertz. I can increase UCC SDT. That means I can take care of the triple excitation. It increases the number of parameters drastically. So it has just this number of parameters, say around the blue dots, say just around 100 parameters. The UCC SD. If I go over to UCC SD, the parameter counts increases to 200, but really does not increase your non-parallelity error. The non-parallelity error is still around, say, 2.5 or 3 millihertz. These are our ansatz. Our ansatz is very low, even lower than UCC SDT. And look at the non-parallelity error now. It is almost zero. That is, it uniformly describes the entire potential energy surface through this variational quantum eigensolver algorithm. I'm not going into this thing because this is going into too details, that how much the expressibility of the ansatz, that and how much is the scaling. So more and more expressible my ansatz is, it becomes more expensive, but it becomes also more accurate. But if I cut down the expressibility of my ansatz through, say, through these different approximations, I have a much higher reduction in the number of my quantum gate count and the quantum circuit depth. But as you have seen from the previous slide, the error or the energy really does not deteriorate at all. So with this one, I will conclude my presentation that I have talked about two algorithms. One is the phase estimation algorithm, which is probably beyond the scope of NISQ-WEDA, but at the same time, this is theoretically exact. But the problem is that it requires a very well prepared reference state that actually should have a substantial overlap with your target eigenstate. But we can use, we have actually used this variational quantum eigensolver algorithm to actually prepare this state, done it in a conceptually minimal space with the minimal parametrization. But we can also devise our ansatz in such a way that only within this variational quantum eigensolver algorithm, without really introducing the IQPE algorithm, you can actually design your circuit in such a way that you can uniformly describe your molecular potential energy surface, whether it's a strong correlated regime or a weak correlated regime, with uniform precision. With this one, I just want to acknowledge all the persons involved in this talk, in this work. Dipanjali actually done all these works in this particular topic, in both the topics I have talked about. Dibbendu, Sonaldeep, they are also working on different algorithms in quantum computing, particularly using machine learning based acceleration of quantum this optimization process. And of course, this theory that I originally talked about, this double exponential theory, was originally designed in the framework of classical computer by Onish. And of course, this entire work, this work that I talked about, is being done in collaboration with Dr. Srinivasa Prasanna from TCC Crest. And I acknowledge all my funding sources. And finally, thank you for your attention.
So thank you, Professor Maitra, again. And now the session is open for questions. If you have questions, please.
I don't think there is question.
I think, yeah. So let us again thank Professor Maitra for such an interesting talk, and thank you.
All right. Thank you.